Good afternoon, students. Welcome to the sixth lecture of Unit 1, and today is a Monday. So we are starting R&AC first class in this week. So now we switch on to the lecture 6. What we have discussed some topics in last week, that is Saturday's class. The types of ideal cycles of refrigeration. So in this class we discuss about the two types of cycles, that is reverse carnot cycle and Brayton cycle related problems. Okay, right. So coming to the types of ideal cycles of refrigeration. So in the last class we have stopped the session here. Now we'll see the two types of cycles which are very important for the subject point of view. So here the refrigerator generally use two types of cycles. So here the refrigerator generally uses two types of cycles. One is a reverse carnot cycle and a reverse Brayton or Joule cycle. So here the carnot cycle and the Brayton cycle are generally used for both types of application process, right? So both the cycle produces the cooling effect, but you are having some of the temperature differences and also the working fluid. Okay. So the carnot cycle considered in the refrigeration system is a reverse carnot cycle used for engines. So in the refrigeration cycles, so the carnot cycle is considered as a reverse carnot cycle. So we are using reverse carnot cycle for the most efficient use of refrigerator. But it is only theoretical in this conception, but serves as ideal cycle ever to be achieved in the practice. Okay, so the carnot cycle gives the highest possible efficiency during the refrigeration process. Now we'll see the concept of refrigeration cycle in the next slides. So the carnot cycle is generally having four types of cycles. The carnot cycle is having four types of cycles. The first one is isentropic compression process. The second one is isothermal compression process. The third one is a isentropic expansion process, isothermal expansion process. So here we are having two isothermal and two isentropic. Two isentropic. Okay. Now see the first one, isentropic process. So in this isentropic compression process, the air is compressed isentropically. So here the air is compressed isentropically in the curve 1, 2 on PV and TS diagram. So what we have shown in the last class. And also whenever the pressure is increased from pressure 1 to pressure 2, automatically the volume also decreases, but the pressure increases as well as the temperature also increases. So here no heat is absorbed or rejected by the air. Whereas in the compression process, the air is compressed isothermally as shown in the curve 2, 3. Here the pressure increases from P3 to P2 to P3 and specific volume decreases from V2 to V3. Here the heat is rejected by the air during the isothermal compression process. Next. Third one is isentropic expansion process. So in this expansion process, what happens here, the volume increases. Whenever the volume increases from 3 to 4, volume 3 to volume 4, thereby the pressure decreases from P3 to P4, and also the temperature decreases from P3 to P4. P3 to P4. We know that the isentropic expansion, no heat is observed during or rejected by the air. Next, fourth cycle is isothermal expansion process. Here, here the pressure of air is decreased from PT to P4 to P1, thereby the volume increases. So generally keep in mind, whenever the volume increases, pressure decreases. Whenever the volume decreases, pressure increases. Okay. Now, so by taking the derivation, already we have discussed in the last class. So the work done during the cycle per kg of air is equals to heat rejected minus heat absorbed. That is Q1 minus QA. That is equals to Q2 minus 3 minus Q4 of 1. Q4 of 1. Now see here, T2 heat rejected T2 S2 minus S3 minus T1 S2 minus S3, that is equals to taking common T2 minus T1 S2 minus S3. Therefore, the COP of refrigeration system working on reverse carnot cycle is equal to heat absorbed by work done, that is equals to QA by QR minus QA. QA means 4 minus 1 divided by Q2 minus 3 Q4 minus 1. So therefore COP of R is equals to T1 by T2 minus T1. Right? Keep this formula in mind whenever we are solving the problems. Now we'll solve the first problem and we'll do some of the problems. So the two refrigerators A and B operates in series. Now see the problems, very simple problems, straight problems. The two refrigerators A and B operate in a series connection. The refrigerator A absorbs the energy at a rate of 1 kilojoule per second from a body at a temperature of 300 Kelvin and rejects the energy as a heat to a body at a temperature T. The refrigerator B absorbs the same quantity of energy which is rejected by the refrigerator A from a body at the temperature T and rejects the energy as a heat to the body at a temperature 1000 Kelvin. If both the refrigerators have the same coefficient of performance, then calculate the temperature T of the body, the COP of the refrigerators, and the rate of energy is rejected at the heat to the body at 1000 Kelvin. Now see the solution. So what is the given data here? The energy A absorbs, the refrigerator A absorbs the energy Q1, 1 kilojoule per second. So if the body at the temperature of T1 is equals to 300 Kelvin, 300 Kelvin. Next. Now what is the T2 here? The refrigerator B absorbs the same quantity of energy, therefore Q1 is equal to 1 kilojoule, and which is rejected by the refrigerator A from a body of temperature T2. Therefore T2 is equals to temperature T. Now T3, energy as a heat of a body at a temperature 1000 Kelvin. T3 is equals to 1000 Kelvin. T3 is equals to 1000 Kelvin. The arrangement of refrigerator A and B are shown in the figure 2.4. Now see here. So you are having two refrigerators. So refrigerator A and refrigerator B. So here, see here temperature T1 300 Kelvin, T2 is equal to T, T3 is equals to 1000 Kelvin. Now what it is saying? Now first find out the temperature T of the body at T to find out cheyali. So generally we know the COP of A. COP of A is equals to T1 by T2 minus T1. Right? Now what is the temperature T1? Is 300. T2 is equals to T. T1 is equal to 300. So keep this as equation 1. Now, what is the coefficient of performance of refrigerator B? COP of B is equals to T2 of T1 minus T2 minus T1. So T2 is equal T2 divided by T3 minus T2. So T 1000 minus T. So this is second equation. Now both the COP of refrigerator are same. So in the question what it is given, the COP are same. Therefore, the equating equations 1 and equation 2. So what we are getting 300 divided by T minus 300 is equals to T of 1000 minus T. Now see what happening. So 300 divided by T minus 300 is equals to T divided by 1000 minus T. Therefore, so keeping a T's aside, so what you are getting 300 into 1000 minus 300T is equals to T square minus 300T. Therefore, T is equals to root of 300 into 1000, that is equal to 547.7 Kelvin. So therefore, we got the temperature T2. అర్థమైందా? అర్థమైందా? Now, what is the next thing you are having? So first one is completed. The COP of refrigerator and the rate at which the energy is rejected. Now the COP of refrigerators. Since the COP of refrigerator are same, substituting the value of T in the given equation 1 and 2, simply we get the COP of A. Now what is the COP of A formula? Is equal to COP of B formula. Therefore, ఏదో ఒకటి తీసుకోండి 300 divided by T minus 300. Therefore, 300 divided by what is T here? 547.7. So substitute here 547.7 minus 300, that is 1.21. Now what is the third thing? Rate at which the energy is rejected as a heat to the body at 1000 Kelvin. So therefore the work done at refrigerator A, the work done W is equals to rate at which the energy అంటే work done అనమాట. WA is equals to refrigerator A కాబట్టి Q1 divided by COP of A. Therefore, what is COP here? Now WA is equals to Q1 by COP of A. So the Q1 is equals to 1 divided by COP of A is equal to 1.21. That is equals to 0.826 kilojoules per second. Now the heat rejected by the refrigerator QT is equals to Q1 plus WA. Okay. So generally heat rejection is equals to W is equals to Q2 minus Q1. సో మనకి ఇక్కడ Q2 కావాలి, ఎనర్జీ రిజెక్టెడ్ కావాలి. So Q1 plus WA, that is equal to 1 plus 0.826, that is equal to 1.826. Now the work done at refrigerator P, WB is equals to Q3 minus COP of B. Therefore 1.826 divided by 1.21 చేస్తే మీకు 1.51, that is equals to Q3 is equals to Q2. So here heat rejected at the body is 1000 Kelvin అన్నాడు. Therefore Q4 is equals to Q3 plus WB, that is equal to 1.826 plus WB we got 1.51, that is equal to 3.336 kilojoules per second. So this is a rate at which energy is released. Energy means the Q4. So like this you have to calculate problems for the heat rejection at 1000 Kelvin. So hope you understand the problem, right? See here. So in the main exam also, you will get this type of problems. వస్తుంది వస్తుంది అట్లా దోమ వస్తుంది. So the third one, the rate at which the energy is rejected as a heat to the body. Heat rejected అన్నప్పుడు నెక్స్ట్ ఎనర్జీ అంటే Q2 or Q4 అలా వస్తుంది. So here you are getting Q4 answer. So that's why we know the refrigerator COA work done is equals to, so energy, right, heat rejected divided by COP of A. So 1 by 1.21, that is equals to 0.826 kilojoules per second. Therefore, the heat rejected by refrigerator A is equals to QT is equals to Q1 plus WA. So Q1 is equal to 1 and 0.826, that is equal to 1.826. Now the same thing refrigerator B. ఇక్కడ ఏ దగ్గర తీసుకున్నాము, ఇక్కడ బి దగ్గర తీసుకుంటున్నాం. See here, ఏ అయిపోయింది, ఇక్కడ బి. Q3 by COP B. So 1.826 divided by 1.21, that is equal to 1.51. The heat rejected to the body at 1000 Kelvin Q4 is equals to Q3 plus WB, that is equal to 1.826 plus 1.51. So still more joining. Okay. Next. Next is the second problem. A cold storage plant is required to store 20 tons of fish. A cold storage plant is required to store 20 tons of fish. The fish is supplied at the temperature of 30 degrees centigrade. The specific heat of fish above the freezing point is 2.93 kilojoules per kg Kelvin. The specific heat of a fish below the freezing point is 1.26 kilojoule per kg Kelvin. The fish is stored in a cold storage which is maintained at 8 degrees centigrade. Cold storage temperature is minus 8 degrees centigrade. The freezing point of fish is minus 4 degrees centigrade దగ్గర freeze అవుతుంది అన్నమాట. Therefore, the latent heat of a fish is 235 kilojoules per kg, and if the plant requires 75 kilowatts to drive it, then find what the capacity of a plant. Second one, time taken to achieve the cooling. Okay, so the first one is the capacity of a plant, the second one is time taken to achieve the cooling. The assumed actual COP of a plant is 0.3 of a carnot COP. So that is a assumption to be done. Now see the solution. So write the given data first thing. So what is the total cold storage plant is required to store 20 tons of fish. So M is equals to 20 tons of fish. Ante 20 tons means 20,000 kilos. Therefore, the fish is supplied at a temperature of 30 degrees. So the second fish is the second object. Cold storage is a temperature 1, fish is a temperature 2. Therefore, the temperature is 30 degrees centigrade. Then Kelvin lo convert cheyandi. 30 plus 273, 303 Kelvin. Next, the specific heat of fish above freezing point is, so the specific heat above freezing point CAF is 2.93. Next, the specific heat of fish below the freezing point is below the freezing point. CBF is equals to 1.26. Now, the fish is stored in cold storage. So, cold storage ante temperature T1. So, the temperature anta T1 is equals to minus 8 degrees centigrade. So, plus 73, that is 265 kilowatts. Sorry, Kelvin. Now, the freezing point of fish. So, freezing point of fish is normal temperature of fish is 30 degrees centigrade. Freezing point అనేసి వచ్చేసరికి T3 is equals to minus 4 degrees centigrade. So minus 4 plus 273, 269. Next, the latent heat of a fish. So H of Hg of fish is 235, and the total plant requires how much kilowatts? Power is equals to 75 kilowatts, that is equal to 75 kilojoules per second. So first, if you write the data correctly, then automatically 50% answer you can achieve. So see here in the question, which one is T1, which one is T2, which one is T3. Based on that, you can solve any problem, right? Next. So what is the question given? The capacity of a plant. So the capacity of a plant, we know that the COP is equals to carnot COP is equals to T1 of T2 minus T1. COP is equals to T1 of T2 minus T1. That is equal to T1 and 265. 303 minus 265, it is already directly given in the question itself. Now, then actual COP. Actual COP is equal to 0.3% of whatever the answer you achieved. So 0.3 of 6.97. That is one of the clause during the derivation. Okay. So actual 3 COP is equal to 0.3 into COP of, yeah. Now the heat removed by the plant. So heat removed by the plant and actual COP into work required. So what is the actual COP? So this is actual COP, and what is the work required? In the question, 75 kilojoules per second. Therefore, 2 into 0.091 into 75, that is equal to 1.68 kilojoules per second. Right? 2.09 into 75, 156.8. So then convert cheste 156.8 into 60, that is equal to 9408 kilojoules per minute. Therefore, the capacity of the plant is equals to, so the capacity is heat removed divided by 210. So why it is kilojoules per minute? So 210 is equals to TR 1 ton. 1 ton is equals to 210 kilojoules per minute. That is a standard formula or equation you have to get. Okay. Now 9408 divided by the 1 ton, that is equals to 210, 44.8 tons. That is the capacity of the plant with the 75 kilowatts of energy. Now what is the second thing? It is given time taken to achieve the cooling. So assume the actual COP of the plant is 0.300. So 0.3 అన్నప్పుడు actually ఈ question లో actual what is the actual COP? 0.3 of carnot COP అన్నాడు. That's why, so ఇక్కడ problem లో 0.3 actual COP is equal to 0.3 of carnot cycle. Now the time taken to achieve the cooling. So we know that the heat removed from the fish above the freezing point. So heat removed is equals to Q1 is equals to M into C of after freezing T2 minus T3. So directly substitute 20,000, 2.93, 303 minus 269. So substituting, you are getting the value of approximately 2 into 10 to the power of 6 kilojoules. Similarly, the heat removed from the fish below the freezing point. So ఇక్కడ above the freezing point, ఇక్కడ below the freezing point. Qt is equals to m into CBF T3 of T1 20,000 into 1.26 of 269 minus 265. Got it? So below the freezing point is m of CBF T3 minus T1. For substituting the value is 20,000, 1.26, 269 minus 265. That is equals to the big stupid. So 269 minus 265. So the answer is 0.101. So ఇక్కడ వచ్చేసి heat removed from the fish above freezing point. Here heat removed from the fish below the freezing point. Therefore, the total latent heat of the fish Q3 is equals to m into h of latent heat. Therefore, 20,000 into 235. 20,000 into 235. 235 ఎక్కడ వచ్చింది? 235 is in the question itself. See here, this one. Latent heat of fish is 235 as ఇక్కడ ఇచ్చాడు. Okay. Therefore, you are getting 4.7 into 10 to the power of 6. Now, what is the total heat removed by the plant? So, manaki you got Q1, you got Q2, you got Q3. Therefore, the total heat removed by the plant is equals to Q1 plus Q2 plus Q3. That implies Q1 value, Q2 value, Q3 value. Age key site. So Q1 plus Q2 plus Q3. So we are getting approximately 7 into 10 to the power of 6 kilojoules. Therefore, the time taken to achieve the cooling, total heat removed by the plant divided by heat removed by the plant per minute. And the total amount of heat removed by the plant divided by amount of heat removed per minute. Therefore, what is the total amount of heat removed? 6.793 10 to the power of 6. 6 or 5, 6 divided by the heat removed by the plant per minute. So heat removed by the plant per minute is the capacity is this one, 9408. So therefore dividing this into by this, you are getting 700 ml, that is 12.03. Understood? So this is a way of doing the problems for this Carnot cycle. Next, third problem. 500 kgs of fruits. So this problems definitely will get in your main exam, and the mid exam also definitely I will give similar types of problems only the values changes, but only the thing is you have to practice the problems along with R&AC, other subjects with whatever you are having in this session, right? Next, 500 kgs of fruits are supplied to the cold storage at 20 degrees centigrade. The cold storage is maintaining at 5 degrees centigrade. The cold storage is maintained at -5 degrees centigrade and the fruits get cooled to the storage temperature in 10 hours. So here the capacity of a storage is -5 degrees and the fruits get cooled within 10 hours. How many fruits? 500 kilograms. So the latent heat of freezing is 1.105 and the specific heat of fruit is 1.256. Now what is to find? Find the refrigeration capacity of the plant. Now see the problem here. First write the given data. M is equals to 500. So here 500 kgs అన్నాడు కాబట్టి m is equals to 500. Now what is the cold storage capacity? Cold storage capacity is 200. Now this one common. Next, so you got 273 20 degrees, that is 293 Kelvin. Now the cold storage is maintained at -5 degrees, therefore T1 is equals to -5. -5 plus 273, that is 268. Now the fruits get cooled at storage temperature in 10 hours. Now the latent heat is 105, therefore the latent heat HF is equals to 105 kilojoules per kg. Therefore CF is equals to coefficient of performance is equals to 1.256. Okay, 1.256. So it is given in the question itself. Now find the refrigeration capacity of the plant. So total refrigeration capacity of the plant. Now the solution is heat removed from the fruits in 10 hours. So 10 hours lo how much amount of heat is removed from the fruits. So heat removed Q1 is equals to M of CF T2 minus T1. Therefore 500 into 1.26 into 293 minus 268. So finally you are getting 15.700. That is heat rejected from the fruits in 10 hours. Now the latent heat of heat freezing. So freezing Qt is equals to M into latent heat. 500 into 105. So 105 eక్కడ వచ్చింది? This is a 105. That is 52,500. Therefore the total heat removed in 10 hours. The total heat removed in 10 hours is equals to Q is equals to Q1 plus Q2. That is 15,700 plus 52,000. That is 68,200. That is the total heat removed in 10 hours. So what is the refrigeration capacity? So the refrigeration capacity is equals to total heat removed in 1 minute. Therefore 68,200 divided by 10 into 60. So why here 10? So 10 hours kabatti 10 hours into 60 minutes. That is 113.7 kilojoules per second. Then the refrigeration capacity of a plant is 113.7 divided by